Hello everyone, my name is Karla Rojas and I'm a student from telecommunications. I'm going to talk about the transmission media selection criteria. So let's start. We can start by making categories of media. First of all, we have the conducted media, and secondly, we have the wireless media. When we want communications for a given application, for this selection we must find the most effective transmission system, which is made in the context of a number of key design considerations. As you can see, we have a list which includes bandwidth, error performance, distance, security, cost, applications, mechanical strength, physical dimensions, and speed of employment. Bandwidth refers to the raw amount or capacity that a medium can support. After that, we consider the error of performance, which refers to the number or percentage of errors introduced in the process of transmission. After that, we have distance, which may refer to the number of maximum and minimum spatial separation between devices over a single link, and it must not be confused with the end-to-end circuit distance. Security is important for the application. We refer to the protection of data from interception as it traverses the network. Cost reflects the amount of money we're gonna need not only to buy all the equipment but also to maintain it. For applications, we will prefer a transmission system which has a greater number of applications than only one application because it will result in a more useful system. Another parameter we should consider is the mechanical strength, which applies especially to the wire systems such as twisted pair, coaxial, and fiber optic cables, which we will explain later. We should also consider physical dimensions as a special parameter because we need to know the shear weight of a cable, the bulk diameter, and all these properties of cables mostly and systems which allow us to know the area we need to install them. An example of these are the radio antennas, which may take some time to install, but once they are in place, the time required to configure and reconfigure the connections between them can take little time. And finally, we have the speed of employment. In this video, we are going to explore 5 different transmission media. First of all, we will explore the characteristics, benefits, and technical issues we can experiment with this technology. After that, we will explore coaxial cable, microwave radio, satellite radio, and fiber optics. We're going to start with the twisted pair communications. These were almost used exclusively for telecommunication networks for over 80 years. The early metallic electrical circuits were one wire, supporting two-way communications. The first twisted pair introduced was in 1881 by John G. Carty, a young American bell technician and one of the original telephone operators who suggested the use of a second wire to complete the circuit. Initially, to produce these cables, they used uninsulated galvanized iron and then steel telegraph wires were used. Nowadays, we use copper because it is a much better choice for a number of reasons, including its malleability and electromagnetic energy conductive properties. A twisted pair involves two copper conductors, generally solid core, although a stranded wire is used occasionally in applications that require additional flex strength. Each conductor is separated by an insulator or dielectric, which could be made by polyethylene, polyvinyl chloride, or Teflon, which are some of these dielectric materials. The biggest issue with this twisted pair is that for some applications it involves multiple pairs, and then length can become an issue. It aggravates in voice application, crosstalk renders, data communications, and other difficulties. For this technology, bandwidth depends on several factors, including the gauge of the conductor, the frequency of the signal, the nature of the dielectric insulating material, and the length of the circuit. Twisted pair cable is especially susceptible to the impacts of outside interference as the lightly insulated wires as antennas. UTP is perhaps the most distance-limited of all these media options. As distance between network elements increases, attenuation increases, and error performance degrades at a given frequency. We can also say that this technology is an insecure transmission media. While it is relatively simple to place a physical tap on an UTP circuit, it is also fairly simple to detect the presence of this tap. One of the main benefits of this technology is the cost. Acquisition, deployment, rearrangement costs are very low, at least in inside wire application involving a few pairs of these cables. In high-capacity long-distance applications, however, the relative cost is very high due to the requirements for trenching or boring, placement of conduits or poles, and frequency splicing of large multi-pair cables that tend to be relatively short in length. Now, coaxial cable is a very robust shielded Cooper cable. The center conductor is much thicker than a twisted pair conductor, and it is surrounded by an outer shield conductor that serves to greatly improve signal strength and integrity. It was invented in AT&T Bell Telephone Laboratories in 1934, and the first coaxial cables were hollow tubes about 1/4 inch in diameter. This technology acquires its name because two conductors share a common axis, hence we have the term coaxial. Same as twisted pair technologies, this bandwidth depends on several factors, including the gauge, the nature of the dielectric insulation, the length of the circuit, among others. Because of its bandwidth characteristics, it is often used as a high-capacity application such as data and image transmission. Coaxial also offers different limitations in distance because the thicker center conductor offers less resistance to the signal, and transmission can be made over a significant distance. In terms of security, coax is a very secure technology since it's really difficult to place physical taps on a coax without detection. This transmission system is considered expensive in comparison to the one we saw before, and it is used in high-capacity data applications, and however, its positive performance characteristics can outweigh that cost. Microwave radio is a form of transmission that uses ultra-high frequencies that were developed out of experiments with radar during the period that preceded the World War II. These microwave systems are point-to-point radio systems operating in the gigahertz range. The wavelength is in the millimeter range, which is to say that each electromagnetic cycle or waveform is in the range of a millimeter, which gives rise to the term microwave. Such high-frequency signals are very susceptible to attenuation. They must be amplified if they are analog or repeated if they are digital. For the configuration of these systems, we use antennas centered with reflective dishes which are attached to structures such as towers or buildings and generally take the shape of a parabola or a horn. While antennas offer a quite small range, large horns collect more incoming signals and therefore they have a greater gain or increase in signal power. This technology offers substantial bandwidth and also an excellent error performance assuming proper systems design and deployment. Physical obstructions must be avoided at all costs because of the phenomenon of Fresnel zones. Microwave radio also is particularly susceptible to environmental interference such as haze, smoke, fog, and precipitation. Microwave clearly is a distance-limited technology, especially at the higher frequencies. This could be mitigated through a larger antenna and antenna arrays incorporating spatial density and frequency diversity to increase the quality of a collected signal. Some of their disadvantages is that they are really insecure networks and the acquisition, deployment, and rearrangement costs can be high. Microwaves have been used extensively for long-haul voice and data communications. They are also preferred for cable systems due to their relatively high speed and low cost of deployment. Last, we have satellite radio, which is a microwave transmission system utilizing non-terrestrial relay stations positioned in space, where there is no atmosphere and certainly no ether. The concept was initially offered in an article titled Extraterrestrial Relays. Can Rocket Stations Give Worldwide Radio Coverage?, which was published in Wireless World in 1945 by Arthur C. Clarke. The first active commercial communication satellite was launched in 1962 and it was called Telstar First. It was made by AT&T Bell Telephone Laboratories. Traditional satellite communication systems involve a satellite relay station that launches into a geostationary orbit, also known as Clarke, in honor to Arthur C. Clarke. Such an orbit is approximately 35 kilometers above the equator. At that altitude and in that equatorial orbit slope, the satellite is in synchronization with the revolution of the Earth. In other words, the satellite rotates around the Earth at the same speed as the Earth rotates on its axis. As a result, the satellite maintains its relative position over the same spot of the Earth's surface. Consequently, transmit and receive Earth stations point to a fixed spot in the heavens to establish a communications link, secure in the knowledge that the satellite will be there. Satellite radio signals can propagate infinite distances in the vacuum of space with no signal loss if the radio beam can be perfectly focused. The configuration for this technology consists of antennas and reflective dishes, much like terrestrial microwave, and these dishes serve to focus the signal from a transmitting antenna or to a receiving antenna. The dishes generally are mounted on a tripod or other type of brace with anchors to the earth, a pad, or a roof which attaches to a structure such as a building. We should also mention that satellite transmission is susceptible to environmental interference, particularly at frequencies about 20 GHz. This transmission is really insecure and its acquisition, deployment, and rearrangement is really expensive. We can say that easily, if we need this technology, we'll spend about $200 million, including the satellite and its launching. This large number can be reduced if we can share a satellite between a number of users. For more information, you can consult Telecommunications and Data Communication Handbook by Ray Horak. You can also consult Introduction to Data Communications, A Practical Approach by Albert Stan, or Data Communications, A User's Guide by Sherman Kenneth. So that's it. Thank you very much for your attention.